Okay, so y'all got the email that I sent about appending the lecture notes, right? And so I really should have had this in originally, but this is a work in progress. This is one of my first times teaching this. I'm going to say this course. I mean, I've been teaching multivariable calculus for decades, but this, Math 219 specifically, all brand new lecture notes, and it's this kind of slipped through the gap. So symmetry theorems specifically for line integrals is what I want to start with. And the confusing thing is you have to give separate discussions about scalar line integrals versus vector line integrals, because there's very different answers. So we'll start with scalar line integrals. So for scalar line integrals, the news is good. The symmetry theorem is there, and it's exactly what you would expect. Right? It's just like the symmetry theorem for double integrals and triple integrals. Namely, if you have a function that is odd over, some choice of line, which means exactly the same thing as it does for other contexts. And if your domain, namely the curve over which you're doing your scalar line integral, if that is symmetric over the line L also, then we're done here. This integral is 0, and mic drop, walk away. You don't have to anti-differentiate or parameterize, nothing. Right? Very cool theorem. The usual warnings, both conditions must hold. It's very easy to get excited about the fact that your curve is symmetric, and forget that is nowhere near good enough. The function has to be odd also. So same warning that I gave you for double integrals and triple integrals. Likewise, also, it's got to be the same line for both of those conditions. It's no good for the function to be odd over one line and the curve to be symmetric over a different line. Okay. All right. Okay, so that's the good news. Now, vector line integrals. Bad news. There is no symmetry theorem for, there is no odd symmetry theorem. So you cannot apply odd symmetry for vector line integrals. It just doesn't work. The reason why? Not hard to see, actually. And one of the big ideas is that when you reflect over a line, right, the idea is, what's happening over here and what's happening over here, it's pretty much the same story, and the only difference is that we get a minus sign. Right? That was the kind of the big conceptual, the Riemann sum sort of point of view. So it's just not true in this case, because check it out. Look at the sizes. Let me color code better. If you look at the DS's, right, this ds versus that ds, that's part of what we're going to be doing in our integral. Yeah, those are the same. Sure, you can chop it up so that those pieces are the same size. But look at the tangent vectors. Right, the unit tangent vector, that's part of how we do these computations. Those unit tangent vectors, they're just different. They're not equal to each other like the DS's are. They're not negatives of each other either. Like, you would expect, odd symmetry. Maybe the vector field would need to be the negative or something like that. They're just different. They're irreconcilably different, right? So there is we're dead in the water, right? There is no theorem at all, and there couldn't be. Does that make sense to everybody? Okay. Now I will point out that I was trying to be careful with my choice of words, and I point out that odd symmetry doesn't work. If you're curious, I will point out there is a different kind of symmetry that does work. And frankly, it's more trouble than it's worth, and I'm not going to spend time talking about that theorem, partly because we don't have time, and partly because even if we did, it's just not that useful in practice day in and day out. And it's the kind of thing where you're more likely to, you're going to get yourself into more trouble than you're going to get yourself out of. And so so just point of order. Yes, technically there is a symmetry theorem, but it's different. It's different. It's not what you think, and it's not worth your time. Okay, so next thing in for surface integrals. Oh, and just for dramatic effect here, let me let's see, how do I do this? There we go. For dramatic effect, now notice right? So here's me switching back and forth between these two discussions. See how similar? That's on purpose, right? So it's the same story. Same exact story. Again, we have to distinguish between scalar surfaces, surface integrals, and vector surface integrals. Different story. They're different critters. Right? For scalar surface integrals, the good news. The theorem's exactly what you think. If the function's odd, the surface is symmetric, then you win. Integral is 0. No fuss, no muss. Right? So that's great. The usual warnings. Both conditions have to apply, and you have to use the same plane of reflection for both of them. So, like I say, exactly what you would expect. I encourage and support the idea of using odd symmetry for scalar surface integrals. And again, once we look at the vector form, once we look at vector surface integrals, it's bad news. It just doesn't work. And for morally equivalent reasons. In the same way that it was the tangent vector that was all messed up for vector line integrals, it's the normal vector that's messed up for surface integrals. And take a look. I mean, here's an example, and there's the direction that the normal vector points on, that little piece of surface, and here's the direction that it points on its reflection. And they're just they're different. They're not pointing in the same. They're not the same, and they're not negatives. So there's nothing they're just different. There's no real comparison that we can conveniently make there in the context of trying to make an odd symmetry theorem. So, again, heads up. Don't make the easy landmine to step on is to start talking about odd symmetry with vector surface integrals. And there is no such theorem. It's all nonsense. So, beware. Oh, and then I'll also point out this is specifically about odd symmetry. And for vector surface integrals, there is another different kind of symmetry theorem. And it, too, is more trouble than it's worth. You'll get yourself into more trouble than you'll get yourself out of. So it's not a good topic, I think, for this course. Okay. All right. What do you think? Is everybody happy with that? Okay. So now moving on to 7.3. This is another one of these monster sections. I don't know why the book does this, but this is going to be like, oh my gosh, I don't know, 3 or 4 lectures at least. This is a long section, and right here in the statement of the title of the section is the sort of confession that there's really 2 separate topics here. They could easily break this into 2 sections. Right? Just for comparison purposes, and I think 2 is probably the norm amongst multivariable calculus textbooks, but in my textbook I made it 5 because there's a ton. To be fair, some of those sections are short, but still, it's a lot, right? So we're going to be in 7.3 forever, at least a week. Oh, and then of course next week we have Thanksgiving break, and so that means it's okay. So we got today, then we got Monday of Thanksgiving week, and then the week after that. Right? So a lot of time here. Okay, I'm going to do this in a different order than the book does. The book starts with Stokes' theorem, and then secondly goes on to the Gauss's divergence theorem. I'm going to do these in what I think is the more standard, more common order. I'm going to start with Gauss's divergence theorem. I think it's more relatable. It's a good kind of segue in some ways up to talking about Stokes' curl theorem. So anyway, starting with Gauss's theorem. Now I want to flash back here to, here we go, Green's theorem. Y'all remember Green's theorem? And Green's theorem was our first, let's see how to say this, shocker, weird, mysterious magic theorem that involved, my gosh, 2 totally different integrals, one on the interior, one on the boundary. How could this be true? Kind of theorem. So the next one's going to be the divergence theorem, Gauss's divergence theorem that we're about to talk about. The analogies are very strong. They're not perfect. but they are very, very strong. And so I want to point out that the structure, the way I've got my notes written here for Green's theorem, notice we start off talking about what's a boundary. We have to think about orientations regarding boundary. Then we had to talk about this feature of accumulation that I claim is so central to why it works. And then we talked about a related note. I mean, I make the case that then you can talk about the boundary quantity of circulation as actually having location in the interior. You can break it up into little pieces, and we see it on the boundary, but it actually comes from the interior, right? And then there was, as follows from that, we discussed this related notion of circulation density, for which there's a nice formula and a ton of notations and terminology, but point is, simple concept of quantity per unit size. And then putting it all together, we made a theorem. So I'm going to be following that same sort of roadmap to do Gauss's theorem. We're going to first talk about boundaries. Then we're going to talk about accumulation. I'm going to make the observations about boundary quantities having interior locations, which is, again, a little spooky, a little sort of like, but that, are you sure? That seems wrong, right? And then we'll talk about a density and write a theorem. So here we go. Same process. Starting off, Gauss's theorem. Starting off talking about boundaries. Okay. So Gauss's theorem doesn't happen in 2 dimensions, like Green's theorem. Green's theorem is a 2-dimensional theorem. Gauss's theorem happens in 3 dimensions. And specifically, it's about solids, solid regions in 3 dimensions. So that's the first big difference. It's a 3-dimensional theorem about solids instead of a 2-dimensional theorem about 2-dimensional regions. Okay. But still, if you have a solid thing here, and I've got a solid that has kind of a hole in it here, right? There's a bubble inside of this, whatever. It's hard to draw. We can talk about the boundary of that thing. And part of the boundary, of course, is the outside surface. And a lot of people will tell you, slightly sloppily, that the rule for the orientation on the boundary is that it's outward. A lot of people will say it's outward. That's not quite true. What it is it's away from the solid, right? If you're on the boundary, right? If my hand here, if this is the boundary between, I've got solid over here and there's nothingness over here, the rule is wherever your solid is, the orientation, the normal vector for that surface is away from where the solid is and into the nothingness. Arbitrary rule, arbitrary but standard. That's the rule. Away from the solid. Now the reason I say that outward is sloppy and dangerous and not always true is that if you think about it, there's more than just, erase that, there we go, more than just the outer piece of boundary surface. Right? If there's a bubble, right? If there's a hollow region inside of your solid, away from the solid is not outward, it is inward. So that's why you gotta watch out for this outward nonsense. It isn't necessarily outward. It is, however, always away from the solid. How are we doing with that? Does everybody follow? Questions? Everybody's happy? Okay. So just for comparison purposes, remember when we were talking about orientations in Green's theorem, we had a similar sort of like, well, look, there's the sloppy version, and then there's the, let's be careful about it. The sloppy version, when you're talking about Green's theorem, is to say that boundaries are oriented counterclockwise. Not really. On the outer piece of boundary, yeah, but if there's an interior piece of boundary, it's the other way, right? So totally analogous. Just kind of you might say this is a 3-dimensional version, in some sense, of the story we saw with Green's theorem. Everybody see the comparison, how it's very similar? Cool. All right. Right. Okay, accumulation. We need to talk about, first of all, what is the quantity in play? What's the stuff that we're going to be computing? What is the object of this conversation? And it's boundary flux. Now, we've talked about flux previously, right? It's an expression that, loosely speaking, it depends on how your vector field does your vector field have that factor of density stuck in there? But loosely speaking, the idea of flux is it measures, in some sense, how much fluid is passing through your surface. Right? Okay. So boundary flux is exactly what it sounds like. It's flux as measured through a surface that is a boundary of a solid. So, like I say, exactly what you think. Boundary flux, as opposed to, when you're talking about Green's theorem, it was circulation, not flux, circulation that ended up being our accumulating quantity. Here, different context, different story. Here it's going to be boundary flux. Okay, so I claim that boundary flux accumulates. Doesn't seem like it ought to. Boundary surface area sure doesn't. Right? Surface area, if you think about it, is the surface area of this, which is, there's that piece and then there's kind of this piece. That's the surface area of the left side. Plus the surface area of this piece. Well, the surface area of that piece is, it's this area plus that area. Is that equal to the surface area of the whole? Nonsense. The surface area of the whole is equal to what you might call the sum of those two pieces, but then there's these two pieces in the middle. That's not part of the boundary of the whole. And so surface area doesn't accumulate, but boundary flux does. So similar sort of approach to thinking about this. If you look at the left piece, boundary flux, keep in mind, boundary means outward oriented. So boundary looks like that, and then also there's kind of this piece here, all oriented outward. Boundary means outward, away from the solid, in this case outward. So there's the left boundary flux. And now let's look at the right side. The right side, here's part of the boundary, and there's the orientation, again away from the solid, aka outward in this case. Then there's this piece of the boundary of the right side, oriented outward away from the solid again. Right? So we've got our green, the left side boundary flux. We've got our blue right side boundary flux, and when we add them up, you look at what's going on in here in the middle, and all this sort of problematic. This isn't part of the boundary of the whole. But yeah, sure. But look, check it out. It's the same surface, opposite orientations. They cancel. When you add up, they go away. And you are literally left with only exactly the boundary of the whole. Boundary flux for the whole. Does that make sense to everybody? So, again, shockingly similar to Green's theorem. I mean, we're doing Green's theorem. We made a highly analogous argument. It's just that instead of having a shared piece of surface, now is a shared piece of curve. And instead of going through in opposite directions, here we were going along in opposite directions, but it still remains that when you subdivide, you create two terms that have opposite orientations and therefore negative signs of each other, and therefore they cancel. And it's the morally equivalent, exact same story here. Again, not exactly the same. It's appropriate to the context, but it's analogous. Right? Everybody see how this is? I mean, we're following the same roadmap. Yeah? Yeah, okay, and yeah, so, all right, so I claim that gives us this point of view that we can take, and I emphasize can, you don't have to, but it's really, really useful to, and I'm going to say it as if you have to because I really want you to, and technically I guess you don't have to, but anyway, I think it's really useful that you can think of it as boundary flux is distributed over the interior, right? And little pieces of it have location. You can talk about where certain quantities of boundary flux come from in the interior, right? And so, for example, now going back to Green's theorem, I made the case, similar analogous case there, that, let's talk about the outward-oriented boundary flux, the boundary circulation when we were doing Green's theorem, and you can compute that circulation. You get some quantity. The way I've got it written here, it's 33, whatever. But where does that 33 come from? Well, that circulation is the sum of that circulation plus that circulation plus that circulation plus that circulation, etc., etc. Let's see here, plus this circulation, blah, blah, blah. So how much of this 33 came from this red chunk in the middle? How much of the 33 came from in there? Well, that 33 is literally a sum of these 9 numbers. And so whatever the number is, whatever the circulation, boundary circulation is for this piece, that's how much of that 33 came from there. Right? Is that cool? So that's an old concept. I want to remind you again, the really relatable version of this is when I sort of did the same analysis for the fundamental theorem of calculus. And keep in mind, we think of the fundamental theorem of calculus as being a measurement of change. The value here minus the value there. Change, right? And we observe that it's an accumulating quantity. And if you look at the fundamental theorem of calculus, you can make an interpretation that the change accumulates over the interior as described by just looking at little pieces. So I can talk about this total amount of change. I'll do it like this. Total amount of change that happens over this purple interval. You measure it on the boundary. That's not really where the change comes from. The change doesn't come from the boundary. That's a measurement thing. That's not that's not where change happens. If you want to know how much change actually happens on a little sub-interval in here, no problem. How much did the function change? Well, measure it. Right? Do the value here minus the value there, namely that minus that, and this difference. The amount of change that you measure on this little piece, that's how much of the total change happened in this interval. Because the change accumulates, and you can just look, I can literally see the function changing there. So, well, the same thing is true when you're talking about flux. Yeah, sure. We measure flux, outward-oriented boundary flux. We measure it on the boundary. Yeah. Obviously, that's the definition of surface flux. Is it's a vector surface integral over the surface itself. In this case, the boundary. But even though you measure it on the boundary, it is actually a sum of a bunch of little pieces that happen in the interior. And if you want to know how much of what happened, how much of what you detect on the boundary, how much came from inside this little block here, no problem. Just measure the outward-oriented boundary flux on that little block. That tells you how much of what you see in the purple actually came from the green. Right? Just like with the fundamental theorem of calculus, just different quantity, different picture, higher dimensional, weirder, harder to visualize. Same concept though. Okay. All right. So, just like change, just like circulation, boundary flux is kind of a stuff. You can think of it as it's not, obviously it's not a physically solid thing, but it behaves like it is. And so you can treat it like it is. And we are going to. And when you treat it like a physical kind of a stuff, then you get powerful results. Okay, so in particular, here's one thing we do with physical stuff. We talk about density. Right? Again, we're, came into this course perhaps with a very narrow point of view on density as being mass per unit volume. And recall that I've generalized that to quantity, whatever the stuff is. Maybe it's mass, maybe it's population, right? Population density is an easy, relatable example that we're all accustomed to. But the quantity of whatever sort divided by size of whatever sort. And thankfully here we're back to a volume context, so we don't have to, think in those terms. But quantity per unit size is what density is. And this quantity here being mass is why we call this mass density. That's mass per unit volume. Okay, likewise then, there is a kind of density that we can associate to flux. If I think of flux, how much boundary flux comes from a little piece of solid of a certain size. Same notion, just like mass, flux is an accumulating quantity of stuff that I can think of as distributed over the interior. I can talk about then how much stuff there is in any given location, any given little sub-region. And when you have stuff, you can talk about how much per unit size, and boom, we have a new kind of density. Since the quantity is flux, we call this flux density. Is that cool? I mean, it's weird, right? I totally get that it's weird. It takes a little time to kind of digest this stuff, but that's the idea there. Quick reminder, don't forget everything here is being recorded. If you're having a little trouble digesting all of I'm throwing a lot of perspectives at you all at once, right? So lean heavily on the recordings. Come back at the part that you didn't get because I said it too fast. Hit the recording, right? Listen to it again. Come to office hours, go to the help room, and try to get yourself primed to understand, and then listen to it again, right? I'm a big believer. Okay, so flux density. Y'all know that I'm a big pusher of this idea of variations on the concept of density. That said, I want to be clear, this is not my creation at all. This is a very common term. In my second major, physics, when I was an undergrad, I think it's fair to say that I heard the term flux density more often than I heard the sort of the mathematically proper term, which is divergence, which is ultimately what this flux density is. This is where divergence comes from. It is flux density. It's this idea of flux per unit size. So very, very common term to say flux density instead of divergence. And y'all are largely engineers, not all exclusively, I understand, but those of you who are engineers, engineering's not that different from physics. My bet would be you're going to hear flux density a lot, right? So it's a very, very good to be familiar with the term, but also really, it's a wonderful. It points to how you really should think about what divergence is. It's the accumulating quantity of flux per unit size, namely volume. Okay. All right, so here we go. Flux density. It's flux per unit volume. Boundary, of course. Boundary flux. And this flux density is computed with this formula. It goes by the name divergence. We have a couple of different notational options. Div, I think, is pretty easily motivated. Right? It's the first three letters of divergence. I guess you could call it dive. I think that just kind of sounds weird. Everyone calls it div. And then here's this other notation, and y'all will recall this from chapter 3, but del dot. right? This flashback to chapter 3. Recall that if you think of del as being a vector of partial operators, and if you think of your vector field in terms of coordinates, then it really is very much like we're doing a dot product. And, again, a little bit of sloppy interpretation, but it's very common. It's very useful, very convenient. So again, not something I made up. This is very, very standard to write del dot to mean divergence. How we doing? Everybody all right? We're all ready now to state the theorem. I'm not quite going to do it just yet. I want to point a little bit to this idea that divergence, aka flux density, aka this formula, is literally telling you, as it says right here, how much flux per unit volume is happening in a given location. And so just take a quick look. I mean, here's an example. We've got a vector field, and it creates a boundary flux through the boundary of a certain ball. Whatever, it doesn't really matter what that ball is. The point is, there is flux being created by this vector field. Boundary flux being created by this vector field. Which of these points is creating more of that flux? Right? Is there more flux being created here? Is there more flux being created here? Reminder, think about single variable calculus. Okay, here's the fundamental theorem of calculus again. And if I were to ask you, at this point versus at this point, is more change, this accumulating quantity we measure on the boundary, I don't say that wrong, is more of it happening here or here? And obviously when I say change, I don't mean at a single point there's no actual change, right? But nearby, is there more change happening nearby this point or nearby that point? Well, we look at the derivative. We look at the change density. And I can see that has a lower derivative. And this point over here, there is a higher derivative. So at which of these points is there a greater change density? Well, that's that one. Yeah, of course it is. There's just more change happening in the vicinity of this point. And you can see it right there in the picture. And it's geometrically satisfying that derivative, aka change density, is the thing that answers the question. So, by analogy, it's the same story here. We don't look at change density, we look at flux density. For instance, in the creation of flux density answers the question. And so you can compute this out. Now, you've got to do the appropriate partial derivatives, but you can take the partial derivatives of that vector field and add them up, and you get this. Make sure, of course, that you can crank out those partials and that you know the proper formula for divergence. And anyway, there's our flux density, and the values at these two different points are, well, I've got 48 at the first point, and I've got 75 at the second point. And B then is the point where there's more flux being created. Hard to visualize what that means. Hard to sort of see it in the same sense that we see change, right? But it's the same. It's analogous in all those ways. All right, everybody happy with that? All right. So, whoops. Here we go. Here's the big theorem. Then this is Gauss's divergence theorem. It's one of the big theorems from the course. Top two, anyway. Huge theorem, massive applications in physics and engineering. In fact, I had a conversation with some engineering professors a few years ago. We were talking about changes to how we teach multivariable calculus, and I was asking them, what's really important to y'all, right? To the engineering school. What do you really need students to know? And they could not stop talking about the broad term vector calculus, which the two big theorems of vector calculus are Gauss's divergence theorem and Stokes's curl theorem that we're going to talk about next, which will probably be Monday. Anyway, here it is. Again, we've already got the tools. We just have to piece them together. We've talked about flux, boundary flux as being a quantity of interest. Boundary, specifically, we've talked about what boundary means, specifying what the proper orientation is on a boundary. And so boundary flux is a meaningful thing now as we have orientations attached to boundaries. So that was the first thing that we did. The next observation is to recognize that boundary flux, aka flux, is an accumulating quantity. We drew the picture and talked about how, well, cancellation on the interior faces, and it works. Right? It absolutely is an accumulating quantity, and so whatever this grand total is, this grand total flux that you're interested in computing, it's the sum of all the little pieces that you get when you chop it up into little small, teeny tiny little boxes. And now we've got this concept of density that we talked about. If you look at how much flux you have on any given piece, we can talk about how much per unit volume. And, flux per unit volume times volume gives us flux. And so I can rewrite d phi as divergence times dv. And we are done here. We have ourselves a theorem that says that boundary flux is equal to a triple integral of the divergence operator over the interior. Everybody all right? There you go. Gauss's divergence theorem. Okay, so let's see an example. Here we go. So we're going to start with, here's a surface. It's the unit sphere. Okay, but careful now. It does say right here, inward-oriented unit sphere. Now, a lot of students get uncomfortable at this point and say, whoa, are you allowed to do that? I thought it was supposed to be outward. The word boundary means outward. Notice in my description of the surface here, I didn't say boundary anywhere. This is just a surface. Imagine we were in section 7.2, computing fluxes. And we're allowed to orient surfaces whichever way, and for whatever reason here, I want to talk about the inward-oriented unit sphere. Yeah? All right? Okay. So, inward-oriented unit sphere, and let's see, I've got a vector field given. I want to compute that flux, aka that vector surface integral. How are we going to do that? You could do this the old-fashioned way, the 7.2 way. You could parameterize your surface and pull back through the parameterization, right? We spent a bunch of time doing this in 7.2, and you can go ahead and crank it through, and that will work technically, but man, that's going to be hard. Try to think through what would happen when you parameterize a sphere. There's trig everywhere. X is full of trig, Y is full of trig, Z is full of trig. Each of X, Y, and Z, I don't know why my stylus doesn't work well. Each of X, Y, and Z inside of this expression is going to be chock full of trig. This would turn into a nightmare of a vector field when you pull back through the parameterization. So let's call that plan B. So let's hope that we can use the divergence theorem. It says right here, you want to compute a flux. Hey, here's an option. It's a totally different triple integral, different integrand. This thing called divergence. We haven't even computed divergence yet. Maybe divergence is nice. Who knows? We'll see in a minute. But reasonable option. But there is a catch. Reminder, there's a catch with all of these what I like to call boundary theorems or accumulation theorems. For Green's theorem, the catch was, here it is, Green's theorem. The catch was that whatever circulation is that you want to compute, don't forget, it's got to be around a boundary. It's got to be a boundary of a region. This is not some sort of, fussy, subtle requirement. It's got to be the boundary of a region, because that region that it's the boundary of is the domain for my new integral. So, really big deal. It's not that these two integrals aren't equal if this isn't a boundary. It's that there is no double integral over here to be equal to, because there is no region whose boundary is what it needs to be. So, big deal, right? You got to make sure that you're actually talking about a boundary. And same deal here. If this has got to be a boundary, and if it's not, then there is no solid over which to even talk about a triple integral, much less hope that it might be equal to what we're interested in. Is everybody on board? Is really important point, really sticky. A lot of students get in trouble forgetting about this very important point. Okay, so is our surface here a boundary? Sadly, no. Right? Don't forget, our surface is the unit sphere. Yeah, but inward oriented, and that's not a boundary. You can talk about this surface all day long. There's nothing wrong with it as a surface, but it is not a boundary as written. Of course, this is easily addressed, right? The same exact surface but oriented outward is just it's S minus, right? It's just turn the orientation around, put in a minus sign to compensate, right? And this surface, this blue, what I have in blue here, if I can get that to erase, this blue surface is a boundary. No problem. It's the boundary of this ball, of course. Everybody with me? Okay, so we're in business. Step 1. The surface that I was given, I recognize that it's the opposite orientation on something that I like better. And so I say, look, I'm going to trade S for S minus, and here's my minus sign to compensate. Right. Step 2, I want to recognize that S minus is literally a boundary. It's exactly a boundary. So that's a relevant point here. That's one of the big important first steps here. And then, now don't forget that minus sign. That minus sign carries through. And then lastly, here's where I assign, or where I apply the divergence theorem. That in purple there is a boundary flux. And the divergence theorem says that boundary flux is computed by a triple integral of divergence. And again, don't forget that minus sign still carrying through. What do you think? Everybody with me so far? Now, day in and day out, a lot of people are going to write this down as, flux through S, big jump over here to minus sign triple integral divergence over V. I just want to point out there really are 3 separate thoughts that go into this first line, and I think it's in the spirit of communicating your ideas, right? Helping the grader to conclude with confidence that you do understand what's going on, right? Show your work, explain your reasoning, being, of course, where points come from. Stretching it out into 3 separate steps here, I think, is very good for making it clear the point you're making, and why did you do what you did, and this is going to make a happy grader. And again, don't forget, a happy grader is a generous grader. That make sense to everybody? Okay. All right. All righty. Okay, so I don't want to say it's all over exactly, but the most of the fun is over here. We have a triple integral of divergence. Now, to be fair, we do have to compute divergence. I claim it ends up being 3 plus x, and the way you compute that is you take the vector field and you play the game, right? You got to take this big formula and you've got to take the x partial of the first coordinate and the y partial of the second coordinate, etc. Add it all up. Right? So computation to be done there. Again, make sure you can do that. And now we've got ourselves with a much less scary integral looking at here. 3 plus x, not that bad. And not only is it not that bad, and I suppose we could do this with spherical coordinates or something, it's even easier than that. And now this, I like to throw in some old ideas while we're doing new stuff, just as a reminder that those old ideas continue to be useful. And don't forget, you can change an integral with two terms in it into two separate integrals that can be dealt with differently, right? And so this one here, oh, that's easy. That's 3 times the volume of that ball. Nothing to it. Snap. No integration required. It's just it's almost a freebie. And then this integral here, 0 by symmetry, and comes up a lot. You're going to notice, I couldn't hide this if I wanted to, you're going to notice by looking at all my old exams that 0 by symmetry comes up a lot on my exams. And I do that on purpose because that's, I believe, representative of reality, what I'm going to call it. In other words, how you're going to experience it coming up in your future engineering classes or physics classes or what have you. 0 by symmetry it comes up a lot. So be on the lookout for that. And we're done. There you go. Yes?
If we have to do this on the exam, we have to do the little, proving credits.
Oh, about the 0 by symmetry. No, I do have different rules. So the rules that I had for exam 2, if you have to give me all 5 conditions, I relax that at the end of the course because let's see why. Well, because that's also more representative of how you're going to see it in the real world. In future engineering classes, if you have that integral and you say it's 0 by symmetry, then it's cool. As long as it is. Yeah. Right? And so, you don't have to give me the 5 conditions. Anybody else? Okay. All right. Okay, so let's talk a little bit let's see, how much have I got here? I've got 2 minutes left. Let's talk about some physical examples. This isn't a physics class, but I do think it's important to have ways to visualize the math. So, whereas most of the time, math sort of serves physics in the sense that, well, we got a physics problem. Oh, math is going to help us out. Math is the tool that allows us to solve a physics problem. Here it's going to be kind of the other way. I'm going to use physics, real-world physical scenarios, to give us basically visual aids to help us understand, to help us kind of get comfortable with the mathematical ideas that I'm throwing at you. So the first one I like to talk about is a light bulb, and I think this is a really good metaphor, a really good example. A light bulb, and imagine there's the element or the LED or whatever. There's that's the thing the light comes from, whatever that is. And what do light bulbs do? Well, they generate little particles of light called photons, and they're just constantly flying out of light bulbs. So it's literally generating them, right? The light bulbs do not run out of photons. It's making the photons constantly, continually. Right? Does that make sense to everybody? Okay. So, and they're a bunch of little teeny tiny little particles, and they flow like a fluid. And again, I'll remind you, it's weird to think of a bunch of solid, discrete particles and talking about it like it's a fluid, but don't forget, so is water. Water is made up of a bunch of little particles, too. It's just that they're smaller. Right? So, talking about a fluid of photons is a perfectly reasonable thing, and no surprise, those photons flow outward away from the light bulb, and there's the arrows are longer the closer you are to the hot spot, and they're shorter as you get further away. We're using the sort of density times velocity interpretation of a fluid flow here. As the photons get further and further away, they spread out more, and there's literally less photon density the further you get out. So we have longer flow lines close in, shorter flow lines further out. Okay, and you know what? I see now I am already out of time. So so we'll pick up here on Monday. And y'all have a great weekend, and see you Monday. Oh, and don't forget I need to check off some of y'all's